All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 14.2, which deals with the combined gas law and Avogadros Principle. Before we get into the details of these notes, I want to outline a couple of objectives that I have for you and you should be able to accomplish by the end of this video. Objective number 1, state the relationship among temperature, volume, and pressure as the combined gas law. Objective number 2, apply the combined gas law to problems involving the pressure, temperature, and volume of a gas. And objective number 3, relate numbers of particle and volumes by using Avogadros Principle. So we start out here with the combined gas law. And it states the relationship among pressure, volume, and temperature of a fixed amount of gas is seen in a formula. Now, I mentioned before that this can be seen in a formula. And so the formula for the combined gas law is going to look really familiar to those three gas laws that we just talked about in section 14.1. So we have P1 times V1 all divided by T1 equals P2 times V2 all divided by T2. Okay, so with this here, this literally is just putting together Charles, Boyle's, and Gay-Lussac's gas laws all together. And we just combine it, and that's why we got the name combined gas law. Now, just to go over our units here, our P1 is the initial pressure, our V1 is our initial volume, our T1 is our initial temperature, and this needs to be in Kelvin, and then our P2 is our final pressure, our V2 is our final volume, and our T2 is our final temperature, and it must also be in the units of Kelvin. Now, in this combined gas law, we can look at pressure and talk about two things. One, pressure is inversely proportional to volume and directly proportional to temperature. Now, in the combined gas law, we can also talk about volume being directly proportional to temperature. Again, volume is directly proportional to temperature. All right, so by knowing our formula here for the combined gas law, we can actually do and accomplish a lot. In fact, all of section 1 really can be consolidated into this formula here, and I'll show you that in a second. Okay, so what we mean by deriving the combined gas law is basically what pieces and parts make it. And so to get to that point, we're going to break it down. Now, what I want to bring up is this. All gas laws, Boyle's, Charles, Gay-Lussac's, can be derived or found using the combined gas law. So we start with this and we represent if we were at a constant temperature. And what this means here with our combined gas law is this. One, I'm going to start out by writing the formula. So P1 times V1 divided by T1 equals P2 times V2 all divided by T2. Okay? And so if we're at constant temperature, what this means is that T1 is equal to T2. Now, if we have T1 equal to T2, what we can do is essentially cancel out our temperatures. So canceling out here, I'm going to represent this in red. I'm just going to cross out our temperatures. And if we are under constant temperature, we can cancel out temperature, and this means our formula would come to P1 times V1 equals P2 times V2. Okay, so right there, this is Boyle's law. Okay, so from the combined gas law, we have found Boyle's law. And if now we can do a very similar thing with constant volume. And so again, we're going to start out by writing down the combined gas law, which is P1 times V1, all divided by T1 equals P2 times V2, all divided by T2. Okay? So if we're at constant volume here, we would have V1 equal V2. And again, just like I did up top here, I can cross out, if something's equal, one variable's equal, we can cross out that variable. So I'm going to cross out my volumes here. And when I consolidate this, I'm going to rewrite it, and I'm going to have P1 divided by T1 equals P2 divided by T2. Now, right there, by having constant volume and canceling that unit or canceling that variable out, this right here is Gay-Lussac's gas law. Okay, and I'm going to circle these or box them in so we can identify that. And then we can do this one more time for our third gas law we talked about in section 14.1, and that is if we are under constant pressure. So once more, we'll start out with the combined gas law, which is P1 times V1 divided by T1 equals P2 times V2, all divided by T2. And if we're at constant pressure, our P1 is going to be equal to our P2. And so again, because P1 is equal to P2, I can take my red pen and I can cancel these out, and I can rewrite this. I'm going to rewrite this down below here as V1 divided by T1 equals V2 divided by T2. Now, right there, this is Charles' law. And so the point about this is if we know one gas law, the combined gas law, we can find each of these three things. So I know I said before, hey, identify all the variables and things of that nature, but if you just write out the combined gas law, and if it doesn't mention temperature, it says temperature is constant, you can literally just cross out your temperature variables. Or if it says volume's constant, you cross out your volume variables. And same thing with pressure. So no matter what here, you have a place that you can start and you can go to find each of these gas laws. Now, let's try doing a problem where we do use all of the variables of the combined gas law. Okay, so in this problem here, it says a gas is at 110 kilopascals and it's under a temperature of 30 degrees Celsius. That gas fills a container with an initial volume of 2.00 liters. If the temperature inside that container is raised to 80.0 degrees Celsius and the pressure is increased to 440 kilopascals, what is the new volume? So again, we're doing a combined gas law, but really what you can get in the habit of is always writing out the combined gas law, and then if something is constant, you can cross it out. Again, this problem, we're going to use all these variables. Okay, so there is our combined gas law, and we are going to insert our knowns and unknowns. So our pressure, our initial pressure of our gas is 110 kilopascals. Okay, so we have 110 kPa. And our initial temperature of that gas is 30 degrees Celsius. Now remember, the temperature itself must be in units of Kelvin and not Celsius. So what this means is that we have to add 273.15 to the degrees Celsius temperature. Now when we do this, we take 30.0 plus 273.15, we press enter, and we get a value of 303.15. And that would be in units of K for Kelvin. Now our volume, our initial volume here, is going to be in 2 liters. Okay. Now we do the same thing for our second values, or our final values. So our second pressure, when we increase the pressure here, we increased it to 440 kPa. So 440 kPa. And our temperature is raised to 80 degrees Celsius. Again, we can't have a temperature in degrees Celsius, so we have to add 273.15 to convert to Kelvin. And so we end up with 80.0 plus 273.15. We press enter, and we get a value or a temperature of 353.15. And that is in units of K for Kelvin. Now, the new volume is what we are trying to find. So our final volume here, or V2, is our big question mark. Okay, so we have some values that we are going to use. There's a lot of numbers, so I'm just going to highlight or underline here in red all of the numbers that we will utilize. Okay, so we start out, our pressure number 1, or our initial pressure, is 110 kPa times our initial volume, which we scroll over here, V1 is 2.00 liters, and that is divided by our initial temperature, which is 303.15 Kelvin. Okay, this is equal to our second pressure, which is 440 kPa. Okay, so 440 kPa times our volume, which we don't know, so we're just going to call that V2, all divided by our temperature, which T2 is 353.15 Kelvin. Okay, so what I'm going to do is I am going to cross multiply, and I don't want to squeeze all of this information in this space. And so what I'm going to do is I'm just going to grab another sheet of paper. And so what I'm going to do, again, is I'm going to take 110 kPa times 2.00 liters times 353.15 Kelvin. So when I do this and I consolidate this, what I get is this. I get 110 kPa times 2.00 liters times 353.15 Kelvin. Now, I cross multiply my other diagonals here, and so what I'm going to do is I'm going to take 440 kPa times my volume times my 303.15 K. Okay, so when I do this, I am going to end up with this. I'm going to write it a little bit differently, but I'm going to have V2 times 440 kPa times 303.15 Kelvin. All right, so again, I have to get V2 by itself. This time with my values here, I have 440 and 303 attached to V2. I need to divide both of those things. And so how I do this is I'm going to put it in parentheses, 440 kPa times 303.15 K, and I need to divide it on each side. So I'm going to draw a big straight line here, and so I'm going to take this same value here. I'm going to divide each side by 440 kPa times 303.15 Kelvin. And we're going to turn to our calculators. But before we do that, I'm going to put a set of parentheses up top here. So in my calculator, what I'm going to do is I'm going to take parenthesis 110 times 2 times 353.15, close the parentheses, divide it by, new set of parentheses, 440 times 303.15. So 110 times 2.00 times 353.15, close the parentheses, divide it by, open up a new set of parentheses, 440 times our 303.15, close the parentheses, and I press enter. Now, I am going to round to 2 digits here. So when we round to 2 digits, we get to 0.58, or I'm going to round to 2 decimals here. So 0.58 is our value. And now we need to talk about units, okay? kPa and kPa are units of pressure. They cancel out. And then our units for temperature, K and K for Kelvin, they cancel out. And so the only unit that we're left with is liters. So we have 0.58 liters as our second volume. Now, I should have mentioned this when we were going over the problem, but the pressure and the volume, as long as they are the same units, and we see here they're both kPa and kPa, they can work. So we could have atmospheres as long as the second pressure is atmospheres. Same thing with volume. If you have milliliters, you can keep it in milliliters. The only unit that has to be particular is that of a temperature, okay? So just keep that in mind as you solve these particular problems. Now what we can kind of tie in, or what we are going to tie in, is the concept of Avogadros Principle, which, remember, Avogadro was the scientist who gave us his number, which was 6.02 times 10 to the 23rd. And that number represented the number of particles in 1 mole of a atom, or 1 mole of a compound. Okay, so we will transition here. All right, so Avogadro's principle states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. Okay, so that's nice, but we need a little bit more explanation here of how we can tie Avogadro's principle into gases. And so what we do is we turn to the help of the kinetic molecular theory to help explain this particular principle. So if we have particles that are made up of different gases, they can vary greatly in size. And we also have to remember that particles in a gas sample are usually far enough apart that the size of those particles, has very little or a negligible influence on the volume occupied by a fixed number of particles. Okay, so after these last two statements, you may be kind of scratching your head of what this actually means. So let's take this into an example, and let's say in our example we have 1,000 krypton and 1,000 helium gas particles in separate containers. So what we have to remember is this: our krypton are really large particles or atoms. And helium, He gas particles, are relatively small. But according to Avogadro's principle, both gases are going to occupy the same volume. Okay, so the kinetic molecular theory, that assumption that gases are really far apart and their size is virtually negligible, influences this statement right here. 1,000 krypton versus 1,000 heliums, what it's saying is they occupy the same volume. They take up the same amount of space. Now, in reality, if you had 1,000 big pieces versus 1,000 little pieces, you would have a difference in volume, but the way gases behave, it's so minute that we can barely tell a difference. There is a difference, but we can barely tell it. Okay, so using this principle here, we can move into a concept known as molar volume. So molar volume is going to be the volume that 1 mole of a gas occupies at 0 degrees Celsius in 1 atmosphere of pressure. Now, 0 degrees Celsius in 1 atmosphere is what we call STP conditions. And so STP stands for standard temperature and pressure. And so these conditions are 0 degrees Celsius in 1 atmosphere of pressure. So at STP, we have the following conditions here. One is that 1 mole of a gas is going to occupy a volume of 22.4 liters. The other point that we can make here is that any 1 mole of gas is going to occupy the same volume of 22.4 liters. And that statement was determined by Avogadros experiments. Okay, so a couple of takeaways from this. 1 mole equals 22.4 liters for a gas, but only if we're at STP, so we're at 0 degrees Celsius in 1 atmosphere. Any other time, we have to use a little bit different method we'll talk about in the future. But 1 mole equals 22.4 liters. So let's try that out in a couple examples. Okay, so we have an example here that says calculate the volume that 0.881 moles of a gas occupies at STP. Okay, so key thing here, we are at STP. That means we can say 1 mole of a gas is equal to 22.4 liters. We start out these problems exactly like we would start out with stoichiometry. So what we do here is we take 0.881 moles of this gas, which it doesn't tell us what gas we have, and we set up our conversion. Now, just like we did in stoichiometry, remember, diagonal units have to cancel. So because we have diagonals of moles, we put moles down here in the bottom, and we want to get to the volume or liters. Now what we have to do is we insert our numbers. So 1 is associated with moles, and 22.4 is associated with liters. Okay, so all we have to do now is take 0.881 times 22.4 and then divide that by 1. So here we have 0.881 times 22.4. We divide that number by 1, and if we round to 3 total digits, we get a volume of 19.7 liters. And it's as simple as that. The key thing here is you have to be under the STP conditions. All right, let's try another sample here where we got to do a little bit more work. All right, so now we still want to calculate the volume that 2,000 grams of methane, CH4, occupies at STP. All right, once more, we are at STP, so that means 1 mole is equal to 22.4 liters. Okay, that's really, really good. Now, what we need to do is we need to start out and we need to write down what's given. So we are given 2,000 grams of methane. So we're going to write down 2,000 grams of CH4. And we are going to do this. To use this, we have to get in moles first, and we have to cancel our units diagonals. So we have, or we will have, grams of CH4 on bottom, and on top we can get to moles of CH4. Okay, so now gram over mole, or in this case mole over gram, indicates that we need the molar mass. So the molar mass of CH4, I looked it up for you, is 16.04 grams per mole. Again, the 16 number is associated with grams, so in this case it's going to go on bottom. So we have 16.04, and that's for every 1 mole. Now we're not quite done because we want the volume of the gas, and so what we need to do is we need to cancel again our units of moles CH4. And looky here, we can use our Avogadros Principle to put 22.4 liters on top. That is for every 1 mole. Okay, so now what we're going to do here is this. We're going to calculate the top, 2,000 times 1 times 22.4, and then we're going to divide it by the bottom, 16.04 times 1. So 2,000 times our 1 times 22.4 gets us a value of 44,800. We divide that by everything on bottom, so 16.04 times 1. Okay, now we get a value here in our calculators of 2,793 liters. Okay, so that would be 2,793 liters of methane gas, okay, so of CH4. Now, they may, or you may see this rounded to 1 significant digit, and if we round this value to 1 significant digit or 1 sig fig here, it would round to 3,000 liters of CH4. All right, so that's how we would go from grams to our liters. And now we can go one more problem here. And so our final problem says find the number of particles of a gas that has a volume of 3.72 liters at STP. Again, we have STP, which is good news for us. That means 1 mole is equal to 22.4 liters. So we start out by writing down what we have. We have 3.72 liters of a gas. And the first thing that we're going to need to do is we're going to need to cancel liters. And we got to go to moles, okay? Now, the number associated with moles here in our conversion is 1. The number associated with liters is 22.4, okay? We're not quite done because, hey, the problem said the number of particles. So we're going to need another conversion. And we have to think here, well, how would we do that? Well, the first thing we need to do is cancel out moles. And then since we want particles, we can put particles on top. Now this is reaching back to chapter 11 when we introduced the chemical mole. And remember, 1 mole is equal to 6.02 times 10 to the 23rd particles. Okay? So what we have to do here is this. 1 is associated with moles, and then our 6.02 times 10 to the 23rd is associated with particles. So we put 6.02 times 10 to the 23rd. Now, we're going to go to calculate this, but remember, whenever you have scientific notation, you need to put that in parentheses. So what we are going to do is we are going to take 3.72 times 1 times our Avogadros number, which is 6.02, times 10 to the 23rd. We press enter and we divide it by 22.4 times 1, and we press enter. So rounding this actually rounds up to 10.0 times 10 to the 22nd particles. And that would be particles of gas. All right, so we've talked about a lot here with the combined gas law and Avogadros principles. These are key things here with our gases unit. I hope you have enjoyed this episode, and I hope you've learned a lot. And if you haven't already, make sure you subscribe.